Good morning, everyone. And let me start by asking this question. Has any one of you wondered whether you could explore the stars? I have. Ever since I was a child, I dreamt of exploring the stars, venturing for millions of miles into outer space. But growing up in a post-communist country, I soon realized that for a boy, it's probably unlikely to become an astronaut and pilot a shuttle into outer space. And so my dream of exploring the stars became as distant as ever. Until one day, I found out that scientists and engineers have been trying to harness the same fusion energy that powers our stars here on Earth. I was really interested in the field, and I decided that, well, this could be my ticket to exploring the stars. So I studied nuclear physics, and going from Vilnius University to Imperial College London, not before long I knew it. I was there. I stood in front of my first tokamak machine. JET, the Joint European Torus, so far the biggest magnetic confinement reactor in the world. It is humanity's closest attempt to tame the stars and build them here on Earth. I was really excited when I saw this. JET is the Joint European Torus built by collaboration across Europe and operated by Eurofusion, by UK's Atomic Energy Authority on behalf of Eurofusion, sitting somewhere in rural England, in Culham. So not before I know I am working there, and I became really interested in the field. I've acquired some knowledge, and that's why I'm here to share it with you. Nuclear fusion research is really complex. It involves fields from all sorts of industries, from plasma physics, material sciences, radiation damage, to superconductors, superconductive magnets where you can fit a house inside it. I wouldn't be wrong in saying that nuclear fusion research and trying to build a sun on Earth is one of the hardest and challenging puzzles humankind has ever faced. So why are we trying to do that? Why do we want to build such an obscure machine here on Earth? How are we going to do it? And why is it important that we succeed? Well, if we look into energy consumption, we see that we are already consuming a lot of energy, and in an upcoming future, the demand is only going to increase. According to International Energy Outlook, we're going to see an increase of around 56% in the next 30 years, and a 2- to 5-fold increase in energy demand by 2100. So, if we continue to use carbon-based fuels at the rates we are using them now, we're going to experience climate change, we're going to have global warming, and this is something we already see today. If we look into an average number of flood events in US per year, we can see how dramatically that increases over the years. Just this week, we are witnessing the most devastating Californian wildfires, and these extreme heat and wildfires are made worse by climate change. At least scientists say that. So this is a challenge we just can't take lightly. We need a solution for that, and luckily, there has been a lot of progress with renewable energies, renewable energy resources, nuclear fission plants, and carbon capture plants which could provide clean coal energy. However, all of these sources have some sort of drawback, and if we could come up with a solution which could fundamentally have no issues, one which would produce no carbon emissions, do not depend on weather conditions, and unlike nuclear fission, where we split uranium atoms, produce no long-lived radioactive waste, we could fundamentally revolutionize the energy market. And maybe we could have a fighting chance against climate change. Now, that's a tough challenge. And this challenge could perhaps be answered with nuclear fusion. So what is it? Well, we know fusion works. It powers the stars. We see it every day in the sun, when the sun is shining. Here we have an image of the sun. The way it works is we basically fuse two light atoms, such as hydrogen, into a bigger atom, such as helium, and then we end up with a bunch of energy. The process, if we could harness a similar fusion reactor here on Earth, but instead of using just regular hydrogen, we use these heavy forms of hydrogen, tritium and deuterium, we could produce energy for generations to come for approximately 1,000 years. And to put this into perspective, energy from nuclear fusion reaction, fuel found in just 2 lithium batteries of your regular laptop and a bath full of water could provide enough energy for an individual's lifetime, as opposed to 5,000 kilograms of oil equivalent every year. But there's always a but. And nuclear fusion, harnessing nuclear fusion is extremely hard. We need these temperature and density conditions so high that these protons, positively charged protons, would overcome electromagnetic repulsion and fuse into a new atom. In the center of the sun, the entire mass creates enormous density and pressure, with every fusion reaction heating the core temperature up to 15 million degrees. At those temperatures, no material could exist in solid, liquid, or gas state, because everything turns into fourth state of matter, as we know, plasma. Plasma is basically a soup of positively and negatively charged dissociated particles in a very hot state. So how can we confine plasma? How can we confine plasma at this very high temperature when no material could possibly hold it? Well, scientists have an answer. And for the sometime in 1950s, Russian Soviet scientists Andrei Sakharov and Igor Tam was developing a tokamak machine, a toroidal magnetic chamber, which basically confines the plasma in a set of magnetic fields. These toroidal fields you see here, pictured in blue, basically confine the plasma, and the poloidal fields, pictured in gray, shape it and improve its stability. But this is a difficult task. As we try to confine fusion, we press harder and harder on it. We're trying to push on it so that we could create that density, create those temperatures. And it's like basically trying to squash a balloon. You can see here a mass reactor in UKAEA where we're trying to push it, and these magnetic lines, they split, and the plasma becomes unstable and deposits a lot of energy onto reactor vessel walls. So much so that a shuttle re-entering an Earth orbit, we know, we've seen it in films how astronauts experience these heat waves and the entire machine glows in red. This is just 1/10 of what we need to cope. And our group designed and developed components able to withstand 10 times more than the shuttle re-entering Earth's orbit. I was leading the fabrication of these components, which could cope with this heat load. And if we are successful, these components could be used in 2050 in this demonstration fusion reactor, somewhat in the future. Although quite a distant future, but it's very compelling to know that my work can contribute to this huge challenge. So, how many of these challenges have we actually solved? We are able to harness it. We are able to do many things. And over the 70 years period, we've proven we overcome many milestones. To mention a few, JET, the home of Joint European Torus in UKAEA, been able to heat the plasma up to 150 million degrees. That's 10 times hotter than the center of the sun. And JET reaching 150 million degrees makes a rural village in English countryside the hottest place in the solar system. Furthermore, we actually been able to prove that we can create energy from fusion in a tokamak machine, in the toroidal reactor. We were able to prove in 1997 that the fusion energy can produce up to 16 megawatts. Well, we were able to prove that, and it's quite an achievement. However, we were able to do so with 24 megawatts of heating power. So even our best attempt had again a ratio between how much energy we put in and how much energy we get out of 0.64. So even our best attempt is not even breaking even. So we can see that we are still a long way ahead of us. And if you think about it, and according to scientists' predictions, we need at least the gain factor of at least Q, commonly known as Q, of at least 10 to prove that fusion could actually get into a state of burning plasma, and at least 30 to make it commercially viable source. So just as an example, jet is basically like striking a match. It bursts into flame, it quickly disappears. ITER would be like starting a fire, where we have a lot of logs, and they are hot enough to keep on burning. And Demo, this next machine, would be able to use that fire's heat and turn it into energy. So ITER, an experiment like no other, was agreed, this experimental machine was agreed in 1987 by an international collaboration across fusion community. It is being constructed by 7 major players in the world, with entire EU contributing to half of this project, and 6 other members, including Russia, China, US, India, South Korea, and Japan, are working together to build this reactor, a machine of enormous proportion. And the ITER headquarters estimate it to cost around 22 billion. But if we are successful, which we are pretty sure we would, we were able to achieve a plasma state, a state which never been achieved before, the so-called burning plasma state. And if we could do that, we would prove that fusion energy could fundamentally change the world we live in. ITER is hoping to fire its first low-energy plasma in 2025, and should be ready to fire. Should have all the equipment ready by 2035. So still a long time, but we've had a lot of progress in this machine. The next step would be to take the experimental knowledge we have from ITER and turn it into something which could actually provide power to the grid. And ITER itself, although an exciting engineering feat and a project, itself will not solve the global warming, so will not solve the climate change, and will not provide energy to the grid. For that, we need fusion power plants. An organization called Eurofusion unites 28 different countries across Europe, and they are hoping to have a nuclear fusion reactor operating by 2050, firing its first plasma by 2050. There are 28 members, and there's even one in Kaunas, Lithuanian Energy Institute, working already on the reactor design and how that could be used to harness that energy from which powers the sun. Well, if Demo is successful, we will be able to prove that we can tame the star, we can use it to our advantage, to enable our progress, to enable our growth in a sustainable way. And we could actually address the climate change. Although fusion research is really difficult, over the past 70 years, we've had a lot of progress. Although fusion research is really incremental, the results are really slow, we have overcome one challenge after another, and we've reached many milestones. Fusion is publicly funded research. We need people to be aware of that. We need people to want fusion, because we need to build even bigger machines, even larger reactors. And without support, it would be impossible to do it. Without public support, we wouldn't be able to invest in these machines. That's why we want people to be engaged in this research. We want people to know about it, and because it could be our only chance to fighting climate change. Every day I see people working on something they might never see in their lifetimes. The stars here on Earth, bound to our advantage, bound to enable our progress, enable our growth. And you know, that is really inspiring. And I hope fusion research could inspire you, such as it's inspired me. And you know, when I was a kid and dreamt of exploring the stars, that actually happened. So I hope that could be it. That could be explored. That could be inspiring you as well. So thank you.